Hello. Well, I decided to do one more group of problems as a worksheet and as examples because it's the only thing left that I haven't done examples on pretty much. And we've pretty much, in the last four worksheets, it's a pretty decent summary of the whole course. I mean, we didn't do a normal chapter, but like chapter 2, but we pretty much covered that and everything else. And so sampling distribution is the only thing not in there. So I figured, what the heck, I'll include sampling distributions. And one of the gurus said there's a decent chance there'll be a sampling distribution problem. And it is one of the more confused things. Now, so this is a quick run through of it. Certainly I encourage you, if you want, to go back and watch the chapter 7 videos that deal with this, that explain it more completely. But so anyway, I have created a sampling distribution worksheet, and here are problems that are very similar to the ones in the worksheet, that if you have the worksheet, you ought to be able to pay attention to this and be able to do it by looking at these examples. So anyway, so let's talk about what sampling distributions are and do some sampling distribution problems. Marla wishes to estimate the proportion of households in her hometown Oakville that own a cat. Unbeknownst to her, 70% of the households in Oakville own a cat. Marla plans to take a random sample of 300 households and find the proportion that own a cat. Describe the sampling distribution of all possible values of the sample proportion. Now, what that means is a sampling distribution is this. If we assume that 70% is true, like that. Now, when Marla takes a sample of size 300, even if she takes a random sample and does an unbiased sample, she's going to get a p-hat that's probably going to be somewhere around 70%, 0.7, but it's going to be a little bit off just because of sampling variability. So maybe it's something like that. Now, a sampling distribution is based on the concept of, what if we did this many, many times and took many, many samples and got many, many different p-hats? Every time, pretty much, we would get a different p-hat, and those p-hats would vary. And this family of statistics, this family of p-hats, is what we call a sampling distribution. A sampling distribution is every value a sample statistic could take in repeated sampling. And anytime you get a sample and get a sample statistic, such as a p-hat or an x-bar, you should think about the sampling distribution. You should say to yourself, this is just one of many p-hats that I could have gotten. These p-hats will be approximately normal as long as what is true? That's right, n times p and n times 1 minus p are greater than 10. In other words, that your sample size is big enough, pretty much. And so in this case, we've got 300 times 0.7, and then 300 times 0.3, and that's 210, and that's 90, and they're both greater than 10. Therefore, they'll be approximately normal. The mean of the p-hats will equal our proportion, 0.7, and then the standard deviation of the p-hats. Let's look at our formula sheet for this. Sampling distribution, sample proportions. The mean of the p-hats will equal p. The standard deviation of the p-hats because the square root of p times 1 minus p over n. And so that is that. And so all that to say, this is to describe the sampling distribution. It is approximately normal, with mean is equal to 0.7. Standard deviation is equal to the square root of 0.7 times 0.3 over 300, which is that. And so, so you could be asked questions about this. You could be asked, why is the sampling distribution approximately normal? And with proportions, the answer to that is because n times p and n times 1 minus p are greater than 10. Okay, that our sample size is big enough. The other thing about sampling distributions that you have to realize is, in order for this formula to work, what has to be true? We've said it many times. What has to be true for this formula to work? The formula for the standard deviation. That's right. Our population size has to be at least 10 times our sample size. Or as your book says, your sample can't be more than 10% of your population. So we have to assume that there has to be at least 3,000 households because we aren't using, in essence, sampling with replacement here. So that's, and describing a distribution. How do you describe a distribution? You remember how to do that from chapter 1? That's right, cussing. You cuss. Center, unusual value, shape, and spread. Center, and describing center is just taken care of by the mean. All right, unusual values, approximately normal, takes care of the shape and the unusual values, actually. And then this takes care of the spread right there. So that would be describing the distribution. Then the next question is, what's the probability that Marla's sample portion will be greater than 74%? Okay, well, that would be going back to those p-hats again. There's 0.7. So what's the 0.74? Let's say it's somewhere up here, 0.74. If you randomly select one of these p-hats, what's the probability you're going to get 0.74 or more? And how can we find that? Remember the function that tells us the area of a normal curve? Remember that function we've done many times? That's right, normal CDF. And so we'll do normal CDF of, and then 0.74 to infinity, mean of 0.7, standard deviation of that, and make sure to label those lower bound, upper bound, mean, standard deviation. Let me remind you, we've done normal CDF many times. What the heck, we'll do it again. All right, so remember, so we would go second distribution, right there by the vars button. So we go second distribution, normal CDF is that one there. And so we're going from 0.74 to infinity, so I'll just put 9 trillion or something like that. And then the mean is 0.7. And then the standard deviation, you can just put the square root of, and just 0.7 times 0.3 divided by our sample size, which is 300, like that, close parentheses. And there we go. There's our answer. And so that's how you do that. That is a sample and distribution problem. And then it says this. It says if Marla increased it should be her. I think Marla's female. Marla increased her sample size to 500. What's the probability that the sample portion will be greater than 74? Well, it's the same problem, but now your sample size has gone from 300 to 500. We've increased our sample size. Now our p-value, and anytime you use normal CDF, you're in essence finding a p-value, is down to 0.025. And so the relevance of this, as you know, is that this is sort of the basis of a hypothesis test. It's like we're testing this 70% figure. And we got 74% in our sample. Does that provide us evidence against the 70%, or is it plausible that that difference is due to sampling variability? Well, in number 2, our p-value is above 0.05, so we would not have reason to doubt that. But in this one, we would. We have increased our sample size, so you know what we did? We increased our power, in essence. Okay, we increased our power, and now we would have evidence to reject the 70%. At the 0.05 level. And so by increasing our sample size, we have decreased our p-value in essence. And then the last question of this part is, why is the answer to why is this answer, number 3, less than that, even though the sample portions are the same? The sample portions are 0.74. The reason is the increased sample size makes our standard deviation go down. We have less variability. And so the way you would word this is the sample size in number 3 is larger than in number 2. So there will be less variability in the sampling distribution in number 3. Thus, values away from the mean, like 0.74 or more, will be less likely to occur in number 3. When you have a bigger sample size, you're going to be more precise. You're going to be more confident that your sample value is going to be closer to the actual population value. And so therefore values away from the mean are less likely. So that's the first thing in regards to sampling distributions, is that's sampling distribution with proportions. Now let's look at a thing with means. So the context here in regards to means is the weights of the cats follow a skewed distribution with a mean of 50 and a standard deviation of 8. Large randomly selects one of the cats. What's the probability that the cat weighs less than 48 pounds? It may be tempting to do normal CDF here because we've done normal CDF so much, haven't we? But guess what? We can't do that because we don't know how it varies. We know it's skewed, but we don't know the distribution. And the only two that we really know how to work with are normal and uniform. Uniform just means going straight across like it's a rectangle. So that's what we would say to that. But now let's look at this. Large randomly selects 40. Now we get a sample size of 40 of the cats from Oakville and finds their mean weight. Describe the sampling distribution. Now, because of the central limit theorem, we have approximate normality. And so what is a sampling distribution? Well, it's this. All right, so it says the mean is 50. So there's the population mean. If we find the mean of weight of 40 cats, we're expecting it to be around 50 because we are getting an unbiased random sample. We're expecting it to be somewhere, but not exactly equal to 50 because of sampling variability. A sampling distribution, just like before, it's every value x bar could take in repeated sampling. And if we took many samples, many samples, in essence sort of every possible sample, if we did that, it would create a family of x bars that we call a sampling distribution. Okay, and so whenever you get an X bar, you should say to yourself, this is just one of many I could have gotten. Okay, and these X bars are going to be approximately normal if what is true? That's right. If your sample size is bigger than 30, or if it said that it varies, or if it said that it varies approximately normally. Okay, and so in this case, we've got a sample size of 40, so we know our X bars are going to vary approximately normal, even though the population itself is skewed. Okay, and that's what the central limit theorem is. The central limit theorem says is the sampling distribution, or your sample statistic, will be approximately normal, all right, as long as your sample size is large, bigger than 30, so, or if we know the population varies approximately normally, with a mean of that. And then, so what is our standard deviation? So for means, it says sample distribution for means. You notice the mean of the X bars is equal to mu. The standard deviation of the X bars is equal to sigma over the square root of n. So the population standard deviation over the square root of n. And so, and in this case, we're given the population standard deviation. And by the way, this is something that we've mentioned, when we did inference, the difference between this problem and the ones we did later in the year when we couldn't use a normal curve, we had to use a t-distribution, was the fact that we know sigma here. Whereas in like chapters 10 and 11, we didn't know sigma, so we had to use S in its place, and this became a t-distribution. But I don't want to start rambling too much. So how would you describe this sampling distribution? All right, it's approximately normal because our sample size is bigger than 30 by the central limit theorem. The mean will equal to the population mean, which is 50, and then the standard deviation will be sigma over the square root of n, so it's that. And so there's our sampling distribution. That's how our X bars are varying. And so then it says this. It says large randomness selects 40. What's the probability? It will be less than 48. So 48 is somewhere down here. So if you randomly select one of these X bars, what's the probability that you're going to get one of these that's less than 48? What should we do there? That's right, normal CDF, just like what we did before. So we'll do normal CDF from negative infinity to 48. There's our mean, there's our standard deviation. And we get that. It's close. It's not statistically significant. Alpha is equal to 0.05. It's close, but it wouldn't give us reason to doubt the 50 figure. Okay? Whereas if it was below 0.05, we would have reason to doubt the claim of 50 that's given in the problem. But then guess what? If we increase our sample size to 50, all right, so now, all right, so, and finds their mean weight, what's the probability the sample mean will be less than 48? Now, same thing, but now we change the sample size to 50, and now we get a p-value of that. And that would be statistically significant. That would give us reason to doubt the claim. And so that is, sort of, a sampling distribution. Hopefully you can see how it fits into hypothesis testing, and it also has a relevance to confidence intervals as well. And then just like what before, why is the answer to number 8 less than the answer to number 7, even though the sample means are the same? And it's the same thing. We increase our sample size. So this has the same answer to that other problem we did, problem 4. And number 8 has a larger sample size than number 7, so there will be less variability in the sampling distribution in number 8. In number 8, values away from the mean, like 48 or less, comma, are less likely to occur. And so that is a very important concept in sampling distributions. And then the last thing, and this is the last concept we have that I'm going to try to teach you, and that is the concept of what about if you had two samples, and let's talk about the sampling distribution of the difference, all right, of things. A journalist is studying the difference in the proportion of men in a city that have a college degree and the proportion of women in a city that have a college degree. Unbeknownst to the journalist, 38% of the men in the city own a college degree, while 32% of the women do. If the journalist takes an SRS of 300 of the men and 350 of the women in the city and finds the difference in the proportion that have a college degree, describe the sampling distribution of all possible differences. Well, all possible, let's think about this. And so what he's doing is he's taking a sample of the men, 300 of them, and finding a proportion. All right, and we're expecting it to be somewhere around 38%, but it's going to vary because of sampling variability. All right, and so he's finding a p-hats of men. And then he's taken the women, taking 350 of them, and finding the proportion have a college degree. We're expecting it to be somewhere around 32%, but anyway, but it's going to be different from that because of sampling variability probably. But and so he's doing that. Okay, the sampling distribution is every value that could possibly take. So if we just call this a difference, I'll call that difference hat like that. And we're expecting this difference to be 38% minus 32%, which is 6%. So we're expecting it to be that. But we know because of sampling variability, this, if he does it one time, it's probably going to be off. And if he does it again, he takes another sample of size 300 men, another sample of size 350 women, and finds another difference, he'll get another difference. And then if he keeps doing this and he finds many, many differences, he keeps going on and on, he finds many, many samples, theoretically every possible sample, and he gets all of these differences. This family of differences, you know what we call this family of differences? That's right, a sampling distribution. And this sampling distribution will be approximately normal as long as n times p and n times 1 minus p for both of the samples, all right, are greater than 10, okay? And they will be centered, the mean will be centered at that, and then will be centered at the difference. And then, and then the standard deviation. Well, let's look at this for proportions, and for two proportions, all right, the mean of the differences is just equal to the differences in the two proportions. In this case, 38% minus 32%. And then there's the formula for the standard deviation. It's a little complicated, but there it is. So anyway, and so that's what I got right there. It's going to be approximately normal with a mean of equal to 0.06, and then the standard deviation equal to that. And so that's what that stuff plugged in. And it's approximately normal because, if you're asked that, because 300 times 0.8 and 300 times 0.62 and 350 times 0.32 and 350 times 0.68, all of those are bigger than 10. They all had to be bigger than 10. Therefore, the all possible differences would be approximately normal. And that means we can do normal CDF. And so this says, what's the probability that the difference would be greater than 10%? So 10% or 0.1, somewhere up here. No exactly, but just to orient ourselves. And so somewhere above 10%, what's the probability that you're going to get 10% or more? And what's the function we can use to find that area? What does it say, please? That's right, it's normal CDF. Good job. And so we do normal CDF, and from lower bound, upper bound, that mean, that standard deviation. Make sure to label those, and then we get that. And that's it. That's sampling distributions, and that ought to allow you to do the sampling distribution worksheet, which is one of the most confusing topics we have all year. So anyway, so give the sampling distribution worksheet a chance, and please send me any questions that you have about them. And that's it. I'm not going to send you any other worksheets. At least I don't think so.